And first of all, I want to thank the organizer for inviting me to give a talk at this conference. And my talk is a little bit different from the traditional glycobiology. So there's more chemistry to the talk than biology. So just bear with me for the next 20 minutes or so. So the title of my talk is Design, Synthesis, and Characterization of glycolipids and glycoclusters as molecular gelators. So our research is kind of in the interface of chemistry, biomaterials, and glycolipids, so much more interdisciplinary research than just in a single field. So first of all, what are molecular gelators? So I'll give you a quick overview about the concept, and then I'll show you a few systems that we have been working on in the past few years in my lab, and a quick summary. So the few systems that I'm going to talk about, basically we are going to use monosaccharides, like a very familiar compounds for you guys, glucose, glucosamine. So we use them to make very useful self-assembling materials or glycoconjugates. So molecular gelators are a special type of molecules that they are small compounds, small molecule, usually molecular weight less than 1,000. And they can form gels in organic solvents or water. And the driving force for this kind of gelation is totally by non-covalent forces. So we have hydrogen bonding, peptide stacking, and van der Waals interaction. So because of the driving force are all non-covalent interactions, so the gels formed are totally reversible. So it's unlike polymer gels. So these are a different type of gels, and so they are formed by totally physical forces rather than chemical forces. And the typical preparation is very simple. We dissolve a small amount of material, the gelator molecule, in a solvent, and heat or sonicate to form a homogeneous solution, and let it settle at room temperature for about 15 to 20 minutes, and then they would form this kind of entangled network, and that's what you will see. You invert the gel. When you see no obvious flow, then we would characterize this as a stable gel. So the carbohydrate-based molecular gelators, obviously, carbohydrates are biological origin, and the gels of biological or natural product origins, they would be materials that have potential biomedical applications because of the biocompatibility and also the biodegradability. And hydrogelators, in the polymer hydrogels, they have been widely used or have been explored to be used as scaffold for tissue engineering and drug delivery carriers, and also they have been applied in protein immobilization and separation. And carbohydrate-based hydrogelators, so here what we are talking about are the small molecules rather than the polymer hydrogels like agarose gels. So the polymer-based hydrogelators, basically, they have intrinsic chirality. We can functionalize the molecules specifically, and the products, we are expecting them to have potential biomedical applications. Some of the structure features of low molecular weight gelators that are shown here is kind of very unique type of compound. So this is a system that's in the literature that we worked on many years ago. So you can see that they have a lipid tail, a hydrophobic unit, the pink highlight, and in the blue highlight area you have the polar hydrogen bonding group. And this is a very efficient organogelator, and this is a hydrogelator. So the organogelator typically means that they can form gels both in organic solvents and water. Hydrogelator means they can form gel in just pure water. So the structure feature include hydrophobic unit typically, and hydrophilic or hydrogen bonding unit in the molecule. And so in our lab, in the past few years, that we found very simple modification of the glucose that can result in effective organogelation. So the glucose-derived system, so very simple, we just protect the 4 and 6 position with benzylidine acetal, and then we can functionalize this, the 2 and the 3 hydroxy group with different functional groups, and then we screen the properties of these glycolipids and found very efficient systems, for example, as shown here, when the molecule contains a terminal alkyne group, depending on the tail length from 0 to 4 or so, that typically is 5 carbon to 7 carbon, then the molecules can form very efficient gels in hexane and ethanol and water. Some of the optical micrographs of the gels that are shown here, the dried gels, so they have this they form this kind of fibrous network. So it has refringent property because the molecules are chiral, so they have liquid crystalline properties. And very similarly, it doesn't matter which position the acyl group is. Typically, they form this kind of fibrous network. And some other example, these first two are in water, and then these last two are in hexane. So they all form kind of tubular, or sometimes they have a smaller fiber or longer diameter in very long dimension in one dimension and shorter in the other dimension. So basically, so that's the optical micrographs of these gels in hexane and water. And the scanning electronic micrograph, as we can see that they also form kind of highly porous fibrous network. And when the chain lengths get longer, so this is shorter chain 5 carbon, this is 6 carbon, the fiber become a little bit softer and also thinner in diameter. So these are all the dried hydrogels under the ICEM, so you have to dry all the solvents completely. So our hypothesis for the physical gelation is we have this X-ray crystal structure model of an analog. So basically the molecule form a one-dimensional hydrogen bonding array between the ring oxygen and the 3-hydroxy group. And so basically we have this kind of hydrogen bonding between the different sugar moieties, and the 4,6-benzylidene acetal, the phenyl group plays a very important role in the molecular assembly. So it helps the molecule to form this kind of monolayer, and then further they can pack into bilayer and then into planar sheets. And also the tail is important for the van der Waals interactions. And the planar sheets can further curl and form the helices and the tubules. And then they can form a 3-dimensional cross-linked network that would trap solvent within the network. And that's our mechanism for the gelation. So in our lab, over the past few years, we have studied the different functionalization at the different position of the glucose. And we obtained a very good structure and gelation property relationship, so we know where we can modify the structure to obtain effective gelators. So the next few systems that I just give you a quick summary of the results that we found. So when we add one additional hydrogen bonding unit to the system, then we obtain fairly a more efficient gelation system. For example, we can synthesize carbamide. So you just add an NH, hydrogen bonding donor, into the molecule, and we synthesize this different analog and screen their properties, their gelation properties. And so the carbamides, they are very efficient compared to the ester gelators. So the concentration, what I mean by efficient is that the concentration usually is much lower. So this is in DMSO water about 1.1 milligram per ml. Typically for the ester system, we need about 5 milligram per ml to 10 milligram per ml. And so this is, if it's pure water, that would be 0.1 weight percent. And this is ethanol water gel. That's the ICEM micrograph of the dried gels, so they have this kind of fibrous network. And for the ethanol water, it has similar kind of fibrous feature in the dried gels, and that's the optical micrograph. So you can see that the fibers is growing from the solvent, from the solution, and we can still observe the presence of the solvent. This is not fully dry, so that's kind of confirmed the formation of the fibrous network, and that is the reason that we can obtain this kind of effective gelation system. So some other micrograph, the scanning electronic micrograph, shows that the fibrous feature is not the only feature for the gelators. Majority of them do form fibers, but sometimes they also form planar sheets. And for example, these two carbamates, so they form this kind of little bit thinner kind of planar sheets kind of feature. But this is a scanning electronic micrograph, so I think these are not very high resolution. At higher resolution, we might see some different structure features of each of these little planar sheets. When we introduce some further extra amino group into the molecule, we switching glucose to glucosamine, then we have a built-in hydrogen bonding donor in the molecule, and we synthesize different kind of analogs, like including carbamates, amides, and ureas. So all these reactions are very efficient. You can just do them in a one-step reaction and isolate these materials. And so we found that basically the carbamates, these are the structure analogs of the glucose derivatives. So these unlinked carbamates are also very efficient to function as gelators. And amides and ureas, they are all quite efficient. So ureas have double hydrogen bonding capacity. So in theory, they should enhance the molecular assembly. But in our system, we found that amide and the carbamates, they work just as well as urea. So sometimes it's not the more the better. So it's what's important that you have to have a balance of the different kind of intermolecular forces. So the synthesis I'm going to skip. So basically, we can take the very simple that you take N-acetylglucosamine, do the glycosylation, and then protect the 4,6 position, and then remove the 2 position, and then functionalize it. And so I want to show you some of the results we got from this system. So we found that typically almost all of the functional groups can be introduced into the glucosamine hide group. In the ester system, it's restricted to a certain kind of functional group in the molecule. But in the glucosamine system, basically it's well tolerated. We can have different kind of modifications. So this is an example of the electronic micrograph of this benzyl carbamate, and it has the kind of fibrous feature as well. And this is the ethanol water gels formed by the isobutyl carbamate, and this is a water hydrogel at 4 milligram per ml formed by the same molecule. And the amides are equally efficient. So basically, they formed also kind of fibrous feature. These are the optical micrograph, not the electronic ones. So it's lower resolution. And in ethanol water, you can see that solvent evaporate as we observe under the microscope. But in diamiso water, the fibers are, you can still see the fibers floating on top of the solvent. So that basically, it kind of indicates indirectly that the formation of fibrous network is important for the gelation. So some other system that we have been working on in the past few years is to introduce photosensitive component into the molecule, so then we can use this as biosensor or chemosensors. So a quick overview of the system, the polydiacetylene system. So basically, these are the diacetylene monomers. So when they align properly, they can be polymerized and form a new type of materials. It's called polydiacetylenes. And so the polydiacetylenes, they can change color when you heat them or exposed to toxins or adding different kind of solvents. So it's a very useful system that can be used as chemosensors. So in our lab, that we try to incorporate the diacetylene unit into the sugar hide group so that we can obtain a new type of materials that stimulate responsive kind of materials that they would have two kind of changes. One is phase transition, one is the color transition. So we made this different kind of substituents and we screened their properties, and we found that the long tail lipids are very efficient in forming the gels. So this is the ethanol gel at 10 milligram per ml. Room temperature is colorless white gel, opaque white gel. And treating with UV turns into blue color, and when you heat it, it turns to red color, and this is reversible if the heat is below 70 degrees. And so basically, we found that by incorporating the lipid into the sugar hide group, that we can polymerize the resulting diacetylene lipids efficiently. And so, but in sometimes that we use the very low voltage of TLC lamp, like 6 volts TLC lamp, and it's not fully polymerized. So the red part are polymerized, gray part are not polymerized. So it's partially polymerized polymer. And we need to use a stronger UV lamp in order to cross-link or polymerize the entire system. But some systems that we cannot polymerize easily with the TLC lamp, for example, this molecule, this long-chain lipid. And so basically, it does form gel. However, we cannot use TLC lamp to cross-link it. But what's interesting is that when we remove the methoxy group, the alpha methoxy group, and forming this deoxylipid, then we can cross-link it very easily, polymerize very easily. So this ethanol gel, that it turns to blue color when you treat with UV light, and we observe it appeared blue under this optical microscope as well. And under the IC electronic microscope, we see this kind of fibrous network system. So it's a very small structure change could lead to a pretty big material property change, and that's not unusual to in this kind of molecular gelator system. So some other system that we've worked on, we also incorporate the diacetylene group into the glucosamine hide group, and this did result in more efficient gelator. So these are the field emission scanning electronic micrographs, and they form this kind of smaller fibrous network, and this is the bipolar system that they also form very efficient gels in ethanol, about 1.2 milligram per ml, and they've also formed the kind of fibrous network. So basically, in our lab, as in the introduction, that basically we are synthetic-oriented lab, but we are interested in biomaterial applications and also biological applications for our molecule. And so some other system that we've worked on in the recent few years, a quick summary, that we also studied a different kind of glycoconjugate system. We try to use a UGI reaction, a one-port, four-component reaction that you add an aldehyde or ketone and amine and isocyanate and carboxylic acid, and in the one-port reaction, we can form this kind of peptoid feature, so it's highly efficient reaction. So in our lab, that we use this reaction to study, to incorporate different sugar moiety into the molecule, and we can synthesize different kind of glycopeptides. And we found very interestingly that this molecule also is an efficient gelator, and so this can be synthesized by a one-port reaction, which is quite efficient, and that's the diamiso water gel. Some other system that we work on recently in the lab is we also use the click reaction, that they gave very nice, nice system that worked quite efficiently in diamiso water. So these are the optical micrographs. So they also form the kind of fibrous network. And this is just the very simple glucose derivative, glucose triazole compound. And so we started to explore some of the applications of these gels for drug delivery system. So a particular system that we try to incorporate some acid-sensitive component into the molecule. So, for example, we tested the stability of the gels formed by this compound, and it's quite stable under acidic condition, about 2 days, 48 hours. We don't see much decomposition, but when we introduce a methoxy group into the molecule, then it becomes much more acid-labile. So basically, we could use this system to study control the delivery of certain drug molecules. So, for example, at about 5 hours, it almost decomposed, and at 48 hours, it just fully decomposed. So the mechanism that this portion falls apart under acidic condition, and then the resulting molecule is not a gelator, and that's why we see the homogeneous solution with the residue gel, and the concentration is very low. It's 5 milligram per ml, so it's very small amount of gelator in the molecule. And so we use naproxen as a model system, so we trapped into the gel of this acid-sensitive system, and we monitor that in presence of water, which is neutral condition, at about 9 hours or so, we only see about 50% of the release of naproxen from the gel phase into the aqueous phase. But when we change to acidic condition, then at 9 hours is 100% release of the naproxen. So this kind of shows in preliminarily that we can use these materials for some kind of controlled delivery system, but we can fine-tune the structure to obtain the better materials. And so my lab are currently, we are trying to seek collaborations to use these materials in more biologically oriented system. So I want to give a quick summary of my talk today. So we did a systematic structure and gelation relationship study. I just, for 20 minutes talk, we can't really go into details, but I give you a quick overview. And also I showed you some functional optical sensitive system with containing diacetylene system. They can form gels, and they can have like a two type of phase transition mechanism, and also some pH sensitive system. And for our future work, we are continuing to study the applications of these low molecular weight gelators for stimuli responsive smart materials, and also for controlled release drug delivery system, and through collaborations. And also we are synthesizing glycomimetics and studying their biological applications. Thank you very much for your attention. I would be happy to answer any questions. I timed exactly 20 minutes with this thing. Didn't want to go over the time.
My research is quite interested in doing the design, chemical engineering of designs of polymers to deliver drugs.
Yes.
And as I see here, the hydrogel is probably a problem with terms of biocompatibility, because it has to be at a pH level that would be able to degrade and deliver the drug. In the in vivo situation, in the animal situation, or people, it's usually a neutral. So how do you see this as a translation or application?
So for the for the neutral system, basically you can use these gels for sustained release, because sometimes you don't want like for instance, even Tylenol, they have the time release. Like instead of taking one pill, taking four doses a day, you can take one pill for a day. So the timed release. So in that case, that would be useful, because it can release the content slowly.
If it goes in the stomach, where is the pH?
The stomach would be a different problem. That the pH usually is very low. It's like maybe 1 or 2. Then the system would be delivered. This will be degraded right away. So I don't think so. If we want to have the drug delivered in the stomach, then this will be perfect. Yeah. They can be decomposed in there. But if we don't want to, then this would be a problem. Then we have to come up with a system that do not have the acid-sensitive component in the molecule. But the 4-6 position protected system is sensitive. The last molecule I showed, the triazolipid system, that one is not acid sensitive. So we do have molecules that can respond to different conditions, either acidic or basic conditions.
Okay. In the literature, there's quite a bit of problems in terms of designing delivery systems for drugs. The biggest problem is the encapsulation of the drug into these copolymers, whatever, or the hydrogel you're doing. The hydrogel is more hydrophobic or hydrophilic. And how would you encapsulate the drug into this in order for it as a delivery system? It's a major problem.
That is a big issue in the drug delivery field. So for our system currently, is still kind of at the early stage. So we demonstrated material properties, but we can modify the structure of the materials to target into particular kind of problem. But for your other question, like how to encapsulate them, so one way is to basically if the drug is water soluble, then that'll be the best because most of our hydrogel is very, very low concentration. It's like less than 1%. We don't need much of this material, so which is an advantage because if you have a lot, then it may interfere with the drug performance. So the system is 99% water. So if the drug molecule is water soluble, then they can be trapped into the gel network, into the gel matrix, and we just have to study how fast it's going to be diffuse out, or do we have other mechanism to help it to diffuse? So, but it's something that at the beginning stage, I think we would need a whole lot more study when we really use it. It's nowhere near to the clinical stage.
I'll talk to you over lunch.
Sure, thank you. All right, thanks.
Your gels are not immunogenic. They are not immunogenic. Your gels are not immunogenic, or are they?
I don't think, we didn't test it, but I don't think they should be because they are small molecules and they are not polymers that, and also they may have some toxicity because they decompose into benzaldehyde. But I don't think they should be immunogenic, but they might have toxicity issue that we have to test. But it should be pretty low.
They self-polymerize, so they have the toxicity.
Right, yeah, the polymerized system they would, but for the monomeric system they shouldn't. But that's my
some
my
of
guess.
them you had an alkene group in for something
Alkyne
like
group, yes.
for click chemistry or
Yes,
so, or
right.
polymerization.
Yeah, we
Then
can
it would
do
be
that.
immunogenic, probably.
They would be problem. Okay, all right, thank you.
There are
It's
no
good to know.
further questions. Okay, then I thank you again very much. We are coming to the next talk.
Oh, I forgot about my group. I forgot the acknowledgement to my group, but anyway, they saw my